So this is everything you need to know for the physics regents in one video. So I'm going to start off by describing the differences between scalar quantities and vector quantities because that's often the first question on the regents exam. It'll ask you which one of these is a scalar quantity or which one of these are a vector quantity. So scalar quantities have only magnitude. So they have no direction associated with them, which means that magnitude means that they can be measured, right? The M in magnitude stands for measurement. So for example, I can measure time, right, with a stopwatch, 5 seconds. Does that 5 seconds have direction? No, so it's a scalar quantity. Now, it'll make more sense when I talk about vector quantities. And vector quantities have magnitude and direction to them. So for example, when I say I applied a 5 Newton force, technically that's incorrect because I need to tell you where I applied that 5 Newton force. So for example, let's say I have a problem and it says that I applied, or a student applied, a 5 Newton force on a block, right? That means that the direction of this force has to be in or facing this block. So because it's a force with direction, it has to be a vector, and vector quantities are often forces, right, amongst other things. Let's look at another example, velocity, right? Let's say that a car has a velocity of 25 meters per second heading east. So guess what? That's a vector because it has direction, okay? So there's only 9 vector quantities out there, and that's force, which talks about weight, or which covers weight, and momentum. It's not going to fit on the page, but you guys know that says momentum. And what else? Like normal force. So pretty much anything that has to deal with forces is a vector quantity. Anything that has you dealing with a weight multiplied by, or a mass multiplied by gravity, or a mass multiplied by acceleration is always going to be a vector quantity. Momentum is another vector quantity. You know that impulse deals with force, so it's another vector quantity. And you know that any type of field is a vector quantity. So for example, a gravitational field, a magnetic field, an electric field, they are all vector quantities because fields have direction, okay? So that's scalar and vector quantities reviewed, okay? So if something doesn't have direction associated with it, you know that it has to be scalar, right? Vectors are usually force-based, or when you're talking about speed, it's usually velocity and acceleration. Okay, so let's talk about some other just housekeeping topics like trig functions. So on the physics regents, you'll have to eventually deal with trig functions. So just remember that the sine of theta is equal to the opposite side over the hypotenuse, the cosine of theta is equal to the adjacent over the hypotenuse, and that the tangent of theta is equal to the opposite over the adjacent, right? So sometimes the physics regents will give you, a force diagram that looks something like this. You'll have an object that is launched with a vertical velocity of 20 meters per second and a horizontal velocity of 30 meters per second, and you want to figure out, the resulting vector, like of its direction. So what you can do here is you can always move your vectors around. So you can move this 20 meters per second vector down here, and then solve for the resulting vector, either using a trig function if they give you an angle right here, or by doing a squared plus b squared is equal to c squared. So oftentimes on the regents, you'll be dealt with, or you'll be given these types of situations where you'll draw a triangle and you'll solve for one side, but usually it won't be a clear triangle, so you'll have to move around one of the sides to another side to actually form the triangle like I did here, okay? And this brings me into vector addition. So because vectors have direction, you can always display them as arrows going in a certain direction, obviously. And the length of the arrow kind of dictates its magnitude. So if you ever have two vectors and you want to add them together, for example, this vector plus this vector, what you can do is you can use the head to tail method, right? So you can take one vector, let's say this vector right here, draw it like so, and make sure to keep the scale constant. So on the regents, if they ever ask you to combine two vectors using a ruler, right, always measure out this vector. Let's say that this vector is 5 inches. So make sure that this vector is also 5 inches. And it's in the same orientation. Then draw in your second vector at the end of the first vector. Sorry, that's my alarm. So, all right, the second thing you need to do is you need to draw the second vector on top of the first vector. Okay, so this is my second vector. We have to measure it. Let's say it's 6 inches, and you just draw it on top of here, 6-inch vector. Okay, and finally, with your ruler, you have to connect the end of the first vector with the end of the second vector, right? Like so. And this is going to tell you the resultant vector, right? The resultant vector is it's the result of your addition or of your subtraction, okay? So in this case, we're adding these two, so the length of this vector would be your answer. And oftentimes there's a scale factor associated with it. The Regents will say, oh, well, let's assume that 1 inch is equal to 1 Newton. So in this case, because you're given the scale factor, you would replace your units of measurement, inches, with newtons, right? You would follow whatever scale factor they gave you in this case, which would be newtons. So this would be 6 newtons, this would be 5 newtons, and then you would have to just measure this with your ruler and apply the scale factor. So let's say this came out to be like 13 inches, then that'd be 13 newtons, and the resultant vector would be 13 newtons. You can also add vectors that are flat, right? If you have a vector that looks something like this, let's say that this is a 9 Newton vector, and this is a 3 Newton vector, you can just combine them, move this vector to the end of this vector, and then measure the length of them. You'll get that they're 12 newtons. Now, if two vectors are facing in opposite direction, for example, if this vector in blue is facing towards, the east, and this 3 Newton vector is now facing towards the west, they're going to actually subtract from one another. So you'll find in Regents that whenever two forces are acting in the same direction, or you have two vectors in the same direction, they'll add. But if you have two vectors in the opposite direction, you'll need to subtract them. So the way that you would do this, like graphically, instead of just doing 9 newtons minus 3 newtons, is you would move this vector so that its end is at the end of this vector, like so. So you would just copy it over here, and then you would measure the distance between the tip of this vector and the rest of this vector, right? So you would just kind of exclude this in your measurement. So you put your ruler all the way up to here and start measuring from here. That way it looks like you took out whatever this 3 Newton chunk was. Okay, and your resulting vector would of course be 6 newtons long. Okay, so that's pretty much everything you need to know about vectors, adding vectors, scalars, resultant vectors, addition and subtraction, the triangle method. So you should be covered in that case. Okay, so we're going to go ahead and talk about motion. Okay, so motion, it talks about distance over time, right? D over T. That's going to give you your velocity. And your velocity is essentially how quickly you're moving in a specific direction. Okay, so there's two types of graphs that can come out of this relationship. So the first type of graph is one that gives you distance versus time. And the slope here is going to be your velocity, because remember that the slope is equal to y over x, right? The change in y over the change in x. So in this case, the change in y is a change in distance, and the change in x is a change in time. You're left with distance over time, so this slope has to be your velocity. Okay? Now, velocity is what we use to describe how your distance is changing. So for example, if I have a velocity of 10 meters per second, that's a way of saying that every second that passes, I travel 10 meters, right? My distance changes by 10 meters. Okay, so in 2 seconds, I would have traveled 20 meters, in 3, I would have traveled 30. So that's a way of describing how your distance changes. Acceleration is a way of describing how your speed or how your velocity will change, not just your distance. So another one, or another graph that you can have here is velocity and time, okay? And if you're accelerating, that means that you're changing your velocity. Specifically, acceleration is an increase in your velocity, so your graph will look, again, like a straight line going up, okay? Why? Because in this case, if you increase your velocity over a period of time, that's what acceleration is. Acceleration is measured in meters per second squared, okay? Or meters per second and then another fraction per second, okay? So if your acceleration is 5 meters per second squared, or 5 meters per second, that means that every 1 second that passes, your velocity is increasing by 5 meters per second. Every 2 seconds that passes, well, your velocity has increased by 10 meters per second. Every 3 seconds that passed, you've now increased your velocity by 15 meters per second, so on and so forth, okay? So essentially, what happens here is if you were to plot acceleration versus time, if you were to plot distance over time for an object that's accelerating, you would get a graph that is exponential or exponentially increasing. And that should make sense to you because as what's happening here with distance over time, the slope will be your velocity. And if you take the slope here, the slope of any straight line is the same. But the slope of an exponential curve, well, you can't find the slope because the slope here is always changing, right? You can't use dy over dx. Sorry, that's calculus. You can't use the change in y over the change in x here. Why? Because it's always changing. It's continuously changing. So if you ever have a curved line that curves up or curves down, that indicates that the slope is not constant. So if the slope, which was your velocity, is not constant, it must be undergoing acceleration or deceleration. So deceleration is a change in speed in the negative direction, right? So if your acceleration is ever negative, just know that you're decelerating and that you're slowing down, okay? And oftentimes what happens is you'll be given a problem where you have, a car traveling at, 10 meters per second east, which is this direction right here. And it'll be accelerating at 5 meters per second squared west. What you need to understand here is that when two forces act oppositely, you must make one negative. So before you go into this test, write down a compass rose: north, east, south, west. And just before you do any math, before you open up your page, automatically assign a certain direction a negative value. So assign west a negative value and sign a negative value. That way, if you know something is going west, it's not just going at 5 meters per second squared west, it's going at negative 5 meters per second squared west. So it's actually taking away from your eastward velocity, and that should make sense, right? If you're accelerating backwards, that means that you're decreasing your speed. All right, so just knowing that this direction is negative, this direction is negative is going to help you not get confused when you have like a question about, forces acting in opposite directions, so that you won't accidentally add them instead of subtracting them, or so that you won't accidentally treat this acceleration in the opposite direction of your travel as, an acceleration rather than a deceleration. Okay, so I'm going to quickly go over just some more tricks that you can do with these graphs. So if you have a distance versus time graph, you know that you can find your velocity that way. But if you have a velocity versus time graph, you can find the area of it to find displacement. Okay, so you know that if velocity is equal to distance over time, you know that distance is equal to velocity times time, or velocity multiplied by time. If you look at this graph right here, I have my y, which is my velocity, and my time, which is my x. So if I multiply my y and my x together, aka finding the area underneath this slope, that's going to give me my displacement or my distance, which is d. Okay? So in this case, that should make sense, right? If you were given a graph like this, where you had velocity here and time here, so this is your velocity, this is your time, what can you tell me about my velocity? Well, my velocity is constant, right? It's not changing with time, so this is not accelerating. So what I can do here is I can comfortably take the area underneath this curve. If I'm traveling at 5 meters per second for 5 seconds, then the area underneath here is just 5 times 5, which is 25 meters. That's going to be the distance that I've now covered, okay? So what else can I cover here? Distance, time. If you multiply distance by time, again, you won't get anything, so you never really have to find the area underneath the distance versus time curve. And I think that's it for curves here. Note that if you ever have a graph of acceleration versus time, usually the acceleration is going to be constant, okay? Or it's going to be 0, so it's either there or there. And that's all. Okay, so let's talk about projectile motion now that we have the basics of motion down. So projectile motions, or what a projectile generally is, it's something that is thrown in a certain direction with a certain speed. Okay, which in this case gives us many things to work with. Okay, so when you launch an object or when you launch a projectile, think about like throwing a ball, right? If you throw a ball, it's going to go up in the air and it's going to go back down. Pretty much every single projectile motion question on the Regents talks about that in some sort of way. And there's generally three types. There's one where they say, oh, someone launches an object from ground and it follows this path, and they ask you to calculate a point along this path. Or it starts with someone throwing something off of a cliff like so, right? Or off of a ledge like that. Okay, and then there's another instance where someone throws an object straight up into the air. Okay, and you're trying to find something about that path. So let's talk about the overall arc, because you can see here how this arc is just adapted in different ways for these other problems over here. So what happens is when you launch an object, it has an initial velocity, okay? And in the physics Regents, there's no such thing as air friction or air resistance. So we don't have to worry about any other forces acting on this object other than gravity. And what we do in the physics Regents is we separate the vertical velocity and the horizontal velocity of the object. So for example, if I launch this ball, it's moving both up and to the right of the page, right? It's going up and to the right. That means that it has a vertical velocity that's making it go up. We call this Vy, and it also has a horizontal velocity that we'll call Vx, okay? Because it's going in the x-axis or the x direction, which is left to right. The thing you need to understand here is that Vx is always constant. Okay, so if this object was launched with a horizontal, meaning left-right, a horizontal velocity of 50 meters per second, that means that this object will always be traveling 50 meters per second in this direction until it hits the ground and all that velocity is burnt off. Okay, so it's not like it's traveling 50 and then slowing down. No, in the vertical direction, it's always going to be traveling 50 meters per second. Why? Because gravity doesn't act on this component. Gravity only acts on the vertical component of this velocity. And because there's no air resistance, there's nothing to chip away at the horizontal velocity either. Now, when we talk about vertical velocity, a majority of these problems are going to be about vertical velocity. And that's because whenever you launch something in the air, the force that's acting against it is always going to be gravity. So your vertical velocity, or your Vy, is always going to be decelerated or decreased by gravity. So if I look at this path right here, there's some key points that you need to understand along it. So obviously this is going to be my initial point, okay? And then as this object goes up, what's going to happen to its vertical velocity? Well, it's going to decrease, right? Its vertical velocity is going to decrease because every single object is going to deal with gravity weighing it down and pulling it down closer to the ground, okay? Then at a certain point, gravity will have slowed down this vertical velocity so much that it reaches a point where it's equal to 0. So when your vertical velocity is equal to 0 meters per second, that's when you reach the top or the tip of your path here, okay? So if the problem ever asks you, well, how long does it take for the object to reach the top of its flight path or the top of its arc, you can just find the time where the vertical velocity is equal to 0 meters per second. So you'll be given an initial velocity, or Vi, right? You know that the final velocity at the top of its path is 0 meters per second. You know that acceleration is 9.81 meters per second squared, because that's always just gravity on Earth, and you can solve for time that way, okay? And if they ask you, well, how far did it travel before it reached the top of its path? Well, you know that if you find time, you can multiply time by Vx. So your vertical velocity multiplied by time will give you the distance traveled by that object, okay? So what else? So at the top of its path, you know that its vertical velocity is going to equal to 0 meters per second, but that doesn't mean that gravity is magically turned off at that point. No, gravity still exists. It's 9.81 meters per second squared on Earth, and it's still going to be pushing this object down. How do we know that? Well, it's because the object returns back down to the ground after it reaches the top of its path, right? So after this point, its velocity then turns negative, right? Because let's say that, our velocity started off at 10 meters per second. After 1 second, our velocity will then be reduced to like 0.19 meters per second. And then after this, because remember, gravity is always acting downwards. This is why it was important to draw this compass rose. Because gravity is acting downwards, it should be negative, and it should be subtracting away from your velocity, which is going north or up and is positive, okay? So at a certain point, you subtract enough from your velocity to make it turn negative back into 10 meters per second. And if your velocity is negative, that doesn't mean it's an outrageous answer. That just means that it's going back down south, which is why the object decides to decrease. So that's how you would find that. But the force of gravity is always acting upon it, okay? Same thing goes here. If you ever want to figure out how long it'll take for this object to reach the bottom of its path, you know acceleration is always going to be 9.81 meters per second squared. You know you're usually going to be given the distance that it's falling. You're usually going to be given the VF, or the final velocity as it hits the ground, and from there you can solve for time, okay? Now, a lot of these problems are going to tell you that the object started from rest. And if the object starts from rest, that means its initial velocity is going to be 0 meters per second, okay? So, for example, if this object was sitting at rest on this cliff before it's knocked off, you know that its initial vertical velocity was 0 meters per second before it got knocked off, and then it accelerated downwards, okay? So with these problems, you're always going to be given, or you're always going to be able to kind of derive at least 3 of the 4 variables. And those variables are distance, time, initial velocity, and final velocity and acceleration. Okay, you'll always be able to figure that out, okay? And finally, this last example here, when an object is thrown directly up and they want you to find how long does it take before the object hits the ground again, you know that it's going to be launched with a vertical velocity Vy, and you know that the force acting against it is going to be gravity, which is going to accelerate it downwards back to the ground. So you know that your acceleration is negative 9.81 meters per second squared because it's going opposite the direction of velocity. So you know that at the top of its path, before the object starts heading back down to Earth, you know that its vertical or its final velocity is going to be 0 meters per second, but you'll be given the initial velocity that was launched at, which is going to be, you know, whatever meters per second it is. And from that you can solve for time, or if they tell you the distance that it travels, then you can solve using the distance, okay? So projectile motion is something that a lot of students find tricky, but if you just understand these general forms and what from rest means and what gravity is, it becomes super simple, and I think you guys will do great, okay? So the final type of projectile motion that I kind of covered in a previous part of this video is going to be one that involves trig functions. So for example, they'll tell you that an object is launched with a vertical velocity of 20 meters per second and with a horizontal velocity of like 30 meters per second. And they'll want to know what the angle of launch is, meaning that they want to know like at what angle did the student launch this object. And what you need to understand here is that this is a trig function. If you move this left leg over here, you'll be left with a right triangle. And whenever you're trying to solve for an angle with this setup, you can always use an inverse function. So you can use sine inverse, cosine inverse, and tangent inverse. And what these guys do is they take the opposite side of the hypotenuse and they give you the angle theta. So for example, if I wanted to find the resulting the angle that results from this launch, well, I'm giving an opposite side right here and an adjacent side right here, because this is the side that's opposite, this is the side that's touching my angle, and this is the hypotenuse. So because I'm given an opposite and an adjacent side only, I will then use the tangent inverse. So in my calculator, I'll plug this in and put it over. Well, tangent is equal to the opposite over adjacent, so I'll find the tangent inverse of 20 over 30, and that'll tell me a certain measure angle, or the measure of the angle at which it was launched at, which we'll say is like 30 degrees. Okay, so that's how you solve for that. You could also have a problem, again, dealing with trig, where they'll say that it's launched with a resulting force of 30 meters per second. They'll say that it's launched 30 meters per second, 30 degrees above the horizontal. Find the vertical component of the velocity, or Vy. So again, you know that Vy is here, technically here, and Vx is technically here. But because it's launched 30 degrees above the horizontal, you can move this Vx over here, right? And from here, you're given a hypotenuse, you're given an opposite side, so you can say that the sine of theta, which is your angle, or 30 degrees, has to equal to the opposite of a hypotenuse, or Vy, over 30, and you can just solve for Vy there. Okay, so just don't get confused when you see trig on the test. Just know that it's pretty easy. Oftentimes the solution is literally just to move one of the legs over, and that's pretty much it, right? So those are the two types. Maybe sine functions, the inverse sine functions, sorry, that's another alarm. Maybe sine functions are confusing, inverse sine, inverse cosine, and inverse tangents are or can be confusing for you guys, but once you just know that you just have to plug in the fraction into them and they give you an angle, it becomes pretty easy. Okay, so now let's talk about forces, right? So essentially, if an object is said to be in equilibrium, what that means is that there's no net force acting on that object. So just like something could be accelerated or something could move with a velocity, you can have an object with a certain force to it, okay? So what that means is that this object could be pulled in this direction by a 20 Newton force, right? Is this in equilibrium? No, because there's a net force here. Remember that the net force, or the F net, is the sum of all forces here, or it's just the mass times the acceleration. So if this object weighs 20 kilograms and it's being accelerated by 3 meters per second squared, you can find that the net force here is actually going to be 60 newtons in the direction that it's being accelerated, okay? So that's the net force. Pretty easy. So whenever you're in equilibrium is whenever you're going to have no net force, right? So the way I like to remember it is net force is equal to mass times the acceleration. If you're accelerating, that means you have a net force. So any object that's not accelerating means that it's in equilibrium. So equilibrium means that you have a constant velocity, or that you're at rest, meaning that you have no motion, or you're moving at the same rate, okay? And net force, or when you're not in equilibrium, means that you're being accelerated or decelerated in a specific direction and you're not moving at a constant velocity. Okay, so let's keep talking about this. So in an object, you'll have the force in many directions. The force down is called the force of gravity that's weighing it down. This is also called the what we call weight. So your weight, or the weight of an object, can depend whether based on the gravity of the planet it's on, but the mass of an object is always constant. So the mass is in kilograms always, but the weight is in newtons. So the weight is equal to the force of gravity times your mass, okay? So the force of gravity, or your weight, is always going to be what's holding you down, like so, and the normal force, or the Fn, is just going to be a force that's acting opposite of it, right? But it's not like an object that's on a table is going to magically levitate upwards because of this normal force. That has more to do with when something is in water and whether it's buoyant or not, right? But just know that there's a force that acts oppositely of it, or opposite to it, okay? And finally, over here, you can have, let's say if we were moving this object with a 10 Newton force here, if this was a friction surface, the force of friction is always opposite the force that you're applying. So the force of friction would be found here, okay? And you could always calculate the force of friction as the normal force, or whatever is going upwards like this, multiplied by the 10 newtons, okay? Or the force that it's the normal force times the coefficient of friction. So every single material will have a certain coefficient of friction that tells you, how much friction they'll exert on your object. So the Regents reference table pretty much has all of those coefficients. So if this was like wood, the coefficient would be like 0.71, and you'll just multiply it by the normal force, or the force of gravity, doesn't matter which one you choose to use. Just know that your force of friction has to have the sign that's opposite whatever force is being exerted to pull this object that way, okay? I'll take a minute to pause here and talk about circular motion. If you have an object that's moving in a circular path, just really quickly, you know that it's going to be accelerated, or the force that you're going to feel is towards the inside, or towards the center of its path, right? So this is where the centripetal acceleration is exerted, but the actual velocity is moving in a perpendicular line, right? So the centripetal velocity, right, or your velocity that you're moving at, is always going to be tangent to this circle. So it's always going to be to the left or to the right, but the actual acceleration that you're feeling is going to be towards the inside of the circle. And that should make sense because if you ever drive a car or you're a passenger in a car and someone makes a turn, you're always kind of pulled to the side that you're turning towards. And guess what? When a car turns, right, it's turning around a loop, right? There's technically a circle that's being formed here. Even though the car isn't going in this circle, it's going in part of the circle. So if you were in this car that's traveling this direction, when you turn here, you're actually going to feel a force towards the center of this circle that's forming here, but that the car isn't going along. Okay, so that's circular motion. Let me just think about what else we can go over here. I have a list of topics. I'm just trying to dash through. I work in about an hour, so I want to quickly upload this video for you guys before I go away. Let's talk about inertia. So inertia is the amount of matter, okay, that a certain object has, right? It's dependent on that amount of matter that a certain object has, and the inertia of an object is essentially its resistance to movement, okay? So notice how whenever you want to, push a heavy object, you need to apply a lot of force, right? The fact that object, or the reason why that object wasn't initially in movement to begin with, is because every object has a certain resistance to force or a certain resistance to movement. Okay, that's called as inertia. And essentially inertia is related directly to the mass. So for example, right, and that applies to an object that's in motion and out of motion. So if you have like a 10-pound box, how hard is it, or how hard do you have to push it to set it in motion so that it's moving? Not very hard, but what if you have like a 1,000-pound box, which pretty much is like how much a car weighs? Will you be able to push it? Probably not, right? I'm not calling you weak, but it's going to be a lot more difficult than a 10-pound box, okay? So why is that? Because objects that are at rest tend to stay in rest, okay? That resistance to that force is called their inertia. And the same thing goes for objects that are already in motion, right? If someone slides you a box on the floor, right, that weighs like 5 pounds, is it going to be hard to stop that object? No, right? You can probably like put your foot out and stop that object from moving. Now, what about a train, right? What about like a subway car? What about the E-train? That weighs like probably like 100 tons or like 10 tons or something. Can you stop a train with your foot if it's like moving at a certain speed? No, right? It's going to crush your foot. Why? Because it has greater inertia than you. It has a tendency to stay in motion. So as a result, it's going to stay in motion unless you can match its inertia. Okay? So that's Newton's first law, essentially. Objects that are in motion tend to stay in motion. Objects that are at rest tend to stay at rest. And we use inertia to kind of describe that. Okay? So let's look back at this diagram right here. It's what we call free body diagrams, right? We already talked about when it's at a leveled surface. I just want to talk about whenever it's at an inclined surface. So if you ever have a box on an inclined surface, what's going to be accelerating it depends, right? But what's going to happen here is your force of gravity or your weight is still going to be applied directly downwards. So it's not going to be applied on the slope like this. It's going to be applied directly down towards the ground. So this is going to be your force of gravity or your weight. But your normal or your normal force, your Fn, is going to be directly upwards, and your force of friction is always going to be behind the movement. Okay, so force of gravity is always downwards. The force of friction is always behind. The normal force is always perpendicular to that. And if it's being accelerated downwards, the force at which it's being accelerated is going down here like so. Okay. What else can we say here? So we can also say that the normal force can equal to the mass of the object times gravity times the cosine of theta, where the cosine of theta is going to be the degree at which this is inclined or sloped downwards. Okay, we could also say that the force of the object going forwards can be the mass times gravity times the times the sine of theta. Okay, so that's the force parallel. So that's the force that's parallel to the plane is equal to sine theta times the mass of the object times gravity, whilst the perpendicular force, the force that's perpendicular to its movement, which is going to be this one right here, is going to equal to mass times gravity times the cosine of theta. Okay, so let's look back at this friction force. We already talked about it. It's going to be the opposite of whatever force is being applied or whatever direction you're going to move in. Okay, usually static friction is static friction is what's stopping objects from moving on their own. So for example, like if you have a keyboard on your desk, like I do right now, and if I were like to tilt my desk, my keyboard won't start sliding because it has like these rubber stoppers that add friction. But at a certain point, if I tilt my desk like 90 degrees, my keyboard will slide off no matter how many rubber stoppers I have at the bottom of it, because it reaches its static friction, right? It overcomes its static friction. So if you ever are asked to graph, static friction or the force of friction versus the applied force, I'm just put that AF, but don't simplify it to AF. You'll see that you'll have to apply more and more force until a certain point, and then you have a constant force of friction. So this point right here, that's the force you need to apply to overcome the static friction to set the object in motion. So generally, friction is always a constant force when you're in motion, but when you're trying to get something in motion, the friction force is always increasing. Okay, and to overcome this dip in the graph here is going to be you overcoming that static friction. Okay, and I think we're good on that, right? Let's talk more about gravity really quickly. So I have two formulas for gravity. So the acceleration that two objects or an object experiences due to gravity is given by the formula is just little g, right? Not capital G. This is gravity times, or the gravitational constant times the mass of an object, or mass 1 times mass 2 divided by r squared. Okay, so this is acceleration due to gravity. This unit is meters per second squared. So the way that you would calculate like the force that Earth exerts on an object that's orbiting it would be to take this gravitational constant, which is given in your reference table, multiply it by the mass of Earth, by the mass of the object, and then divide it by the distance between that object and the center of that object. So if they ever ask you like what's the force of gravity, or what's the acceleration due to gravity exerted by the Earth to the moon, you would have to find the distance between the center of the Earth to the center of the moon as your radius, and then multiply that by the gravitational constant and the mass of the Earth by the mass of the moon. Or if you want to say that, an object is 50 meters above the surface of the Earth, or like 50 meters from the center of the Earth, what's the gravitational, or what's the acceleration due to gravity that they experience? Well, you'll put that into r squared. You'll take the mass of the Earth here, and the mass of the object here, and you plug it into this formula. Okay, the second thing is gravitational field strength. Its formula is G is equal to the Fg over m. Okay, so this tells you how strong a gravitational field is, right? So you take the force of gravity and you divide it by the mass of the object to get that, but its units are going to be newtons per kilogram. So the way that you determine which one of these formulas you have to use is based on the unit that they give you. So if on the Regents they tell you, if this is a short response and they fill in the units for you, it's in newtons per kilogram, use this equation right here, okay? Otherwise, if the answer is in meters per second squared, then use this formula up here, okay? Let's see what else we can talk about. Talk about Newton's first law. We can talk about Newton's third law. So Newton's third law is pretty important here. It says that whenever A exerts a force on B, B will exert an equal opposite force on A. So sometimes on the Regents, they'll give you a problem like a baseball is hit by a baseball bat, or a baseball bat exerts a 200 Newton force on a baseball when it's hit. What's the force exerted on the baseball bat by the baseball? And the answer will be just 200 newtons in the opposite direction. What I'm trying to say here is that every action has an equal and opposite reaction. If this ball hits this bat with a force of 200 newtons, first of all, let's look at the direction it's going in, because force is a vector. So that's 200 newtons applied in the west direction. That means that this bat is hitting this ball with the same magnitude, so still 200 newtons, just in the opposite direction. So another example, if I go ahead and I bang my desk right now, my hand is hitting the desk with like 20 newtons of force, and the desk is hitting my hand back at 20 newtons of force. That's why when you hit something, or you like punch a wall, or like you hit a desk, or I don't know, anything hits you, it hurts, right? Because even though you're doing the hitting, the object is technically hitting you back with the same magnitude or with the same force, just in the opposite direction. Okay. What else can we talk about here? Also, when I give you a formula here, just know that it's given to you on the reference table. I would never give you a formula that doesn't exist on the reference table. So just fair warning. You don't have to write any of these down. They exist on your Regents reference table. So, and maybe except for the trig functions, memorize them, but everything else so far has been given to you on your reference table. So let's talk about collisions, because we were talking about forces. So momentum is always conserved. Momentum is given by your mass times your velocity. It's given by this lowercase p. And you know that the momentum of a system before the collision has to equal to the momentum of the system after the collision. So for example, the p before talks about the system, which is the total or the sum of all momentums. Okay, so if you have an object that goes like this, it's 5 kilograms and it's going at 10 meters per second, the momentum of the system here will just be this 5 kilograms or this mass times this velocity, okay? But if you have a second object that's going here and it's 30 kilograms, moving at 5 meters per second, then the momentum of the system will be this 5 times 10 plus this 5 times 30, okay? And there's two things that can happen when two objects collide. It could be sticky, meaning inelastic collision, which means that the two objects continue to move together as a unit. What that means is m1v1 plus m2v2 is equal to m1 plus m2 times vf. This is not given to you. This is something that you can either logic out or that you can just memorize. So m1v1 plus m2v2 tells you the total momentum of the system, right? You'll just have to do that regardless of the problem. But essentially what happens is if the question asks you what is the final velocity of the two objects after their collision, if their collision is inelastic. Inelastic means that these two objects will collide and they will stick together. So you're trying to find the final velocity of these two objects when they're stuck together. So technically the momentum of this system is, well, the mass of this one object now, because they've combined into one, times its final velocity, okay? So elastic collision is the opposite of it, okay? So what that means is if two objects are moving together like so, and they bounce off of one another, and they just move in opposite directions now. So this one is going in this direction, this object is going in this direction away from each other. That's elastic collision, okay? That says that m1v1 plus m2v2 is equal to m1v1 plus m2v2. Right? The only thing that changes here is obviously going to be the sign of the velocity, because now you're going in an opposite direction. So these two boxes were they going towards one another. When they collided, they bounced off of one another and they went in the opposite direction. Okay, so just remember to move the sign around. So if this object has a positive velocity, this object now has a negative velocity. If this one had a negative velocity, it has a positive velocity, because they're changing the direction that they're going in. Okay, same thing with an explosion, right? If something is exploding or being accelerated by a spring, its initial momentum was 0. So you can say that 0 is equal to its m1 and its v1, right? Because if something is at rest, its momentum is 0, right? But all of a sudden, if it's rapidly accelerated, then its momentum is equal to whatever's on the other side, right? So essentially, you're creating its momentum. Okay. You may ask me, well, isn't p before have to equal to p after? Well, technically, the momentum after it's exploded is going to eventually reach 0. But at the same time, some of that momentum is stored within the spring as a different type of energy. So just know that when you have an explosion, right, when something is accelerated by a spring, let's say that you're moving this spring back with a certain velocity and there's an object on the other side of it, the momentum of this object after it's exploded or after the spring goes off is going to be its mass times its velocity, right? Okay, let's talk about springs actually. So springs can store potential energy inside of them. That's given as PE, or potential energy S, the potential energy of the spring. That's just going to be the spring constant, which is K. That just tells you how hard it is to compress a spring, times X, which is the elongation of the spring. Okay, so it's 1/2 kx squared. So x is the difference in the spring's position, aka how much you compress it, multiplied by the k, which is the constant or how hard the spring is. That's the potential energy that's stored inside of a spring. And the force of a spring, the force that the spring exerts, is equal to k times x, right? Okay, let's talk about work. Work and displacement must always be parallel. You know that work is a force exerted over time. So whenever there's movement with a force, you know that there's going to be work that's exerted. Then you want to talk about the total energy of a system. The total energy of a system is, well, what energy can I have? Well, I can have potential energy, can have kinetic energy, I can have gravitational potential energy, and I can have internal energy. Okay, so kinetic energy is movement. Okay, so if you're moving, you have kinetic energy. If you're moving in an environment that has friction, that means that you have internal energy, or Q. Okay, so kinetic energy is movement energy. Q is energy due to friction, right? Or thermal energy, we like to call it. Okay, so when you're moving on a surface that has friction, you're losing some of your kinetic energy in the form of friction, but overall the energy of this system is conserved because energy cannot be created nor destroyed, right? So the overall energy of the system is always going to be the same, even though there's friction, right? It just whatever kinetic energy you lose to friction is just accounted for in this Q value. Okay, then you can also have potential energy in the form of a spring, right? So we know how to calculate that, and also you can have potential energy stored in gravity. Okay, so if an object is held above a surface, a certain distance above a surface, it has potential energy, because if you were to potentially knock this object off, then it can create change, right? Energy is change. Potential energy is stored change. So it's your ability to create change that you kind of store within your system. So technically, this can change its position, thus it has potential energy. It's just due to gravity, okay? And if you want to find the total energy, you add up the spring energy, the internal energy, the kinetic energy, and the potential energy due to gravity, okay? And just a quick note that as an object is knocked off of a ledge, its potential energy due to gravity decreases because it's converted into kinetic energy, which is increasing. So if this object was at rest, obviously its kinetic energy is at zero, right? Because kinetic energy is movement. If you're at rest, you have no movement, so your kinetic energy is 0. But your potential energy is probably going to be a big unit because you have the potential to change your position and to create change. So as this object actually falls down, it's decreasing its potential energy and increasing its kinetic energy. Okay? One last thing I want to just talk about impulse, right? Impulse is just a force exerted over time. So if a question ever asks you, like, what's the total force exerted by a student when he pushes an object at 10 newtons for 5 seconds, well, you just multiply these two to get an impulse, okay? So impulse is just the total force applied over a time. Power is the rate of change of energy. So that's essentially work over time, okay? And that's given in watts or joules per second, okay? Remember that work is given in joules. Any sort of energy is given in joules, okay? And power is given in watts, okay? We now made it past kinematics, so no more movement. We'll talk about electricity. Conductors have free electrons, insulators do not. Okay, objects can only be charged by gaining or losing electrons. So for example, if you have like this negatively charged rod, right? That's because it has gained electrons, right? Protons cannot move in or out of a system, only electrons. So if I have this negatively charged rod and I touch this positively charged object, what will happen here is the charge will balance out between these two. And there's a formula for that that's on your reference table that'll tell you how that force or how that electricity or how that charge cancels out or gets distributed. But essentially, even though this is a negatively charged object, it still has positive charge in the form of protons. It just all the electrons will be transferred onto this object, right? Protons cannot be transferred. We talk about E minus, that's an element, that is an electron, okay? So that's essentially one elementary charge. We know that 1 coulomb is a collection of electrons. So it's many elementary charges. Whenever you see Q, know that the units is coulombs. And if you're dealing with an electron, you have to convert it from an elementary charge to a coulomb, right? Coulombs is just 6.25 times 10 to the power of 18 elementary charges. Okay, So you know that the charge of an electron is, well, -1 of an elementary charge, okay, or -1.6 times 10 to the power of -19 coulombs. So always convert it before you do math with an elementary charge, okay? What else can we say? If you have a negatively charged object, the electric field is going to be towards the center of it. It's going to be pointing inwards. If you have a positively charged object, the electric field is going to be outwards to it. What that means is if you have an electric field, right, a positively charged plate and a negatively charged plate, the force is going to be from the positive end to the minus end, okay? And you can calculate the strength of this force, okay, by Fe, okay, and you can calculate the electric field strength by E, okay? So K Q1 Q2 over R squared. This is the electrostatic force exerted by two objects. You can always find the electrostatic force exerted by two objects by taking the distance between them and the two charges of them, plugging it into this formula, and for this you can take the electrostatic force divided by the charge to get the electric field strength, okay? When you have two objects, right, for example, a plus and a minus charge, you know that the fields will go directly like that. Eventually they'll bend outwards like so, in this direction, right? It's going in the negative side and going out in the positive side. If you have two objects that are like charged, they repel, so they'll actually be going away from one another, like so. Okay, if you have two negatives, they'll also be going away from each other, like so. Just the arrows matter. Remember that arrows go into the negatives and out of the positives, and that likes repel. Okay, so electric potential difference is voltage. That's just the work that's done per unit of electricity. So the movement of electrons is what generates an electric charge, okay? So when electrons move, you get an electric charge and you get a magnetic field, okay? So that's how magnetic fields form, is the movement of electrons, okay? Resistance is, well, your resistance to that flow of electrons. Think about electricity as water flowing through a pipe, okay? The force that the water exerts inside this pipe is your voltage, because that's the work that they're doing, and the volume of water that can pass through the pipe is your amperage, right, which is literally just the charges per second, okay? The resistance is how much water can actually flow through this pipe, however. So if a wire has high resistance, that means that it's a really thin pipe that can't really push or carry that much water throughout it, okay? So resistance is always going to limit the voltage or the amps that can flow through a circuit, right? And those two have a relationship that you can find on your reference table. Okay, then we talk about circuits, okay? Series circuits are always going to have their resistors in a series or in like a sequence, right, where they're on the same line. Whenever you see this array of lines, that's going to be a battery. Okay, so with series circuits, their amperage is always equal to each other, right? So their current is always the same, but their voltage, to find the total voltage here, you'll have to add up the voltage across each resistor. Okay, for a parallel circuit, they're called parallel circuits because the resistors are arranged on parallel lines, or lines that are parallel to one another. So here's one, here's another parallel line, here's another parallel line. Okay, so you can see these lines are parallel versus these resistors are on the same line. With a parallel circuit, 1 divided by the equivalent resistance. By the way, the equivalent resistance is the total resistance in the circuit. So 1 over the equivalent resistance is equal to 1 over each one of these resistors added together. Resistance is measured in ohms, okay? But to find the total resistance of this electric circuit here, that's just R1 plus R2 plus R3. So it's all of the resistors added or combined together, okay? Again, if you want units, you can find those all on your reference table, okay? Let's move on. You can find the resistance over a wire, right, by taking its resistivity, which is just its natural resistance to the movement of electrons, multiplying it by its length and dividing it by its cross-sectional area. So that's how you find the resistance of a wire. If you want a good conductor, you want something that has the least amount of resistance. Okay, I think we covered that in a previous point. Okay, so what else can we go over? You know that resistance is equal to voltage over your current, right? So if you want to graph this, right, you want voltage in the y, current in the x, and your slope will be your resistance, okay? So like I said, an electric current or the movement of any charged particle, usually it's electrons because electrons are the only ones that can really move, is going to generate a magnetic field. Okay, when you have a magnetic field, it's in poles, so you'll have a north pole and a south pole. For two magnets, right, the way that the magnetic field goes is it goes from north to south. So if I drew the magnetic field lines here, it'll go from north to south, from north to south, from north to south, north to south, north to south, right? But if I draw two magnets with the same polarity here, north and north, they'll just go in the opposite direction like this, and they'll most likely wrap around their magnet like so. Okay, so they'll move in this direction towards their southern ends. Okay, like so. Okay, so it's always going from north to south. If you have one bar magnet that just looks something like this is north, this is south, it's moving like so, right, from the north end to the south end. And we actually have a instrument called a compass that will literally point us in the direction that the magnetic field is flowing in, right? So if you were to place a compass here, its arrow faces the same direction as the magnetic field. Okay, so its arrow will be facing towards this way. Okay, which will literally tell you the direction of this field. Okay, so if you have a compass, over here, right, and you have a north plate here and your south plate here, you'll know that because the field goes from north to south, it's going to be facing south, right? You may be asking me, well, aren't compasses supposed to face north? And yeah, you are correct. This is the North Pole and this is the South Pole. But what actually happens is because the compass always points north, that means that the magnetic field of Earth has to be going from the South Pole to the North Pole. And that's because the magnetic poles and the actual directional poles are different. The true, or like the actual North Pole in terms of our magnetic field is located on the South Pole, and the actual magnetic South Pole is located in the North Pole. So the movement of this field, it technically does go from north to south, and our compass points us towards the geographic north rather than the actual magnetic north, which is in the south of the planet. Okay, so let's talk about waves. Okay, we're almost done with this video. So waves, you have different types of waves. You have mechanical waves that need a medium, so they operate by vibrating particles around. An example of this is sound, right? Sound moves air or vibrates air particles to propagate or to continue. And then you have electromagnetic waves, which need no medium. Okay, then you have two different types of waves. You have transverse waves, which are waves that compress one another and go in the left to right direction. And then you have longitudinal waves that go up and down like this, right? Which are perpendicular to the ground that they move on, right? So this is parallel to the ground that they move on, right? Because their movement is like this and the ground is like that. These waves are going to be perpendicular to the direction that they're going in, right? So if they go in the left direction, they're going perpendicular because they're vibrating up and down. If you ever want to figure out which way a particle will move on a certain wave, look at the future, right? Or look at its position in the future. So if this wave is going this way, look in the opposite direction, okay, to a point here. If you follow this wave in the opposite direction, you know that it's going to go down, so the particle is going to go down. Okay, that's just a trick here. Okay, for a transverse wave, it's the particles are vibrating up and down. If you want to know if it's going up or if it's going down, look at the particle or look at the wave or the part of the wave that's the opposite direction it's traveling in. So for example, if this wave was traveling in this direction, right, and you want to know which way this particle will move, well, look in the opposite direction. You know that it has to, the rest of the graph goes up, so this particle has to move up. Okay, let's talk about the actual components of a wave. So I'm going to use transverse waves because they're easier to draw. So essentially one full cycle, don't know why I did it, one full cycle is from, or is going to capture one peak or one crest in one trough. So one maximum and one minimum, and it's going to go back here. So this is one complete cycle of this graph. It captures a peak and it captures a trough. You could, the distance that it takes for this wave to complete one full cycle is the wavelength. You can also find the wavelength by going from peak to peak and trough to trough. So the distance between this peak and this peak is also going to be the wavelength, and the distance between this trough and this trough is also going to be the wavelength. Okay, and essentially the distance that it takes, or the time that it takes for a wave to complete one full cycle, or to go from peak to peak or trough to trough, is the period, and the amount of cycles per second is going to be the frequency. Okay, so the period is always going to have a unit that's different than 1 second, and the frequency is always going to be per 1 second. Okay, so the period can be like 5 seconds or 10 seconds or 11 seconds, but the frequency is always like 5 cycles per second or 10 cycles per second. Okay, so the amplitude then is the distance above and below the midline that the wave will oscillate from. So if the amplitude here is like 5, then it'll go 5 units above the midline and 5 units below the midplane. And the midplane is just, again, that line that it's centered around. So sometimes you can have a wave that's, instead of being centered around the x-axis, can be centered around the y-axis down here. And if you want to graph it, and if it has an amplitude of 5, then it'll oscillate 5 units above this midline and 5 units below this midline, like so. Okay, so another property about waves is that they can either build or they can destroy one another. If you have waves that are in phase, then they'll add to one another. If you have waves that are out of phase, they'll destroy or interfere with one another. So for example, if you have a wave that looks something like this, and you combine it with a wave that looks something like this, because they're in phase with one another for the most part, the resulting wave will just be a combination of both of those wavelengths, of both of those amplitudes. But if you have two waves that are out of phase with one another, for example, like this, here's the midline, by the way, and here's the midline. You see we have a peak here while we have a trough here. Essentially, they're going to cancel each other out, and you're going to have a flat line, because wherever you have a peak here, right, wherever you have a peak here, you have a dip down there, okay, and they're going to cancel each other out. All right. You also know that the speed of a wave is just given by, or the velocity of a wave is the frequency times the wavelength. You know that there's a whole electromagnetic spectrum. Different waves of light can exist in different forms, or different wave and lights exist on a spectrum called the electromagnetic spectrum. You can find that on your reference table. Essentially, waves just have different wavelengths and frequencies that they exist at, and they'll exert different or exhibit different properties at those different wavelengths. Okay, then you have certain properties of light. Specifically, you have diffraction, which is bending around an obstacle, right? So for example, if you have, this barrier right here, this wave can bend around this barrier like so. Okay, that's going to be diffraction. Resonance is when you vibrate something and that causes another object to vibrate, right? Because it resonates with it. The Doppler effect is going to talk mainly about sound waves. It's how sound waves shift around an object that's emitting sound. So if you have an object that is moving in a certain direction and it's emitting sound from the top of it, the sound waves in the front of that object are going to be compressed and are going to have a higher frequency and a lower wavelength. So, lower wavelength, higher frequency. And the waves behind that object are going to have a lower frequency but a higher wavelength. Okay, so this is more high pitched, this is more low pitched. Okay, let's talk about waves in a medium. So when a light hits a surface, it's going to be reflected. Okay, this right here is the normal. So the reflection, or the degree of reflection, or the angle of reflection is going to be equal to the angle of incidence. Okay, so this is the angle of incidence right here. This is the angle of reflection right here. So it's going to be reflected from here to here, and it's always between the normal. Okay, if you want to find how light is refracted, that's how light bends inside of a certain medium. So if this light is traveling like this, always draw a imaginary line like this. This is the normal line. Okay, you're always going to be dealing between an angle between this ray of light and this normal right here. Right, this is the angle of incidence. It's between the normal line and the ray of light. Okay, so essentially this light is then going to bend in some sort of direction, either outwards like this or further inwards like this. And you can measure how much it's going to bend by the angle of refraction, right, which is measured again between the normal and this angle, with normal and this angle. You know that n1 sine theta 2 is equal to n2 sine of theta 1, right? So, or some formula like this that's on your reference table. So the n is the absolute index of refraction. So certain mediums will cause light to act in a certain way when it's inside of them. So that's what n is. There's different values for it. in your reference table, and that's going to affect how light behaves when it enters that specific medium. So check that out. That's what n is equal to. And essentially you can plug it into a bunch of formulas with sine and cosine, or no, with sine and in a bunch of fractions, and it essentially will tell you the extent at which this light wave will be bent in a specific direction. Yeah, that's it. So you know that the speed of light is also constant when we talk about lights. We know that light exists on a spectrum going from radio waves, which have the longest frequency, to ultraviolet rays or gamma rays, which have the lowest wavelength but the highest frequency. You know that the energy of a wave is directly related to its frequency. So the higher the frequency, the higher the energy. And the energy is inversely related to the wavelength. So the higher the wavelength, the lower the energy, and the lower the wavelength, the higher the energy. Okay? So what else can we talk about? You know that in terms of light, purple or blue light is going to have the highest energy, right? And it's going to bend when you pass it through a prism. But again, that's something you can calculate using a reference table, so I don't think it's worth going over here. When something reaches a total internal reflection, that means that all light is reflected at the surface and none is refracted. So it only occurs when light travels from a high to a low index, and the incident angle has to be greater than the critical angle. Okay, so for example, when something is inside of, if a light wave is inside of an object and it just bounces around in this object forever, that's total internal reflection, right? So if you point a laser into a glass box with a bunch of mirrors, okay, the light will just get trapped in there instead of being reflected off, okay? So I wouldn't worry about that. Then we'll just quickly touch base on modern physics before I let you guys go. So we know that light can exist as both a wave and a particle, okay? We know that light, or almost any matter, can be classified into, leptons and hadrons and mesons, right? And everything essentially is going to either be made up from quarks. Okay, so photons are going to be made up of quarks. Electrons are going to be made up of quarks. Okay, so if you consult your reference table, you'll find that it's essentially going to be a tree that organizes matters down like this. Okay, and there's going to be different ways that you can construct matters. So you can have ones made of quarks or ones made up of anti-quarks. Okay, and it'll tell you essentially how you can construct something like this. Okay. In a specific atom, you have a nucleus that's made up of both protons and of neutrons, and then around this nucleus you'll find electrons. What holds the nucleus together is what we call strong force, or strong nuclear force, okay? And E equals mc squared is something that we often use to determine the energy from a certain amount of mass being converted, okay? You know that a proton is made up of an up and a down quark. You know that a neutron is made of an up, a down, and a down quark. You know that quarks have a certain charge to them. So the charge of their particle will depend on the charge of the quarks when you add them all together, okay? So I think that's really it. The last thing I can really touch about here is the atomic spectra, right? So you'll find a graph that gives you like the emissions for mercury and the emissions for hydrogen. It's going to look something like this. This is like n equals 1. This is like n equals 2, n equals 3, and here is the energy level as well. It's going to be like negative 13.0 electron volts, negative 12.0 electron volts, so on and so forth, right? So essentially, electrons exist in orbitals around the nucleus, okay? So sometimes an electron can be excited and it can move into another orbital of the same, essentially of the same, atom, okay? So as you move away from the center, your energy, or the energy of this photon, increases, okay? And as you move closer to the center of this nucleus, the energy will decrease, okay? So each one of these n equals 1, n equals 2, n equals 3, just represents a energy level, okay, that you can exist at. And the higher the n, that means that the further out from the nucleus you are and the more energy you have, okay? So if you ever are moving out, just know that you're absorbing energy, okay, in the form of light. And if an object or an electron is ever moving closer into the nucleus, it's releasing energy in the form of light. Okay, if you want a full review of a physics regents exam, I already have those videos uploaded. If you want to actually apply the knowledge that you've learned into another video, I highly, highly recommend that you guys take a physics regents practice test, or that you watch my videos going over physics regents practice tests, because the best way to study is to actually apply your knowledge into something. But I hope you guys learned something, and I hope you have a nice night.